So this video is goes along with chapter 3, and during this video we're going to talk about equilibrium and static equilibrium, free body diagrams, which we'll abbreviate as FBD, and coplanar force systems and 3D force systems. So the first section we're going to talk about is static equilibrium. It's chapter 3.1 or section 3.1 if you're looking along in your book. And basically with static equilibrium, the main equation that we're going to be dealing with in this class is that the sum of the forces equals mass times acceleration. This is Newton's first law of motion. And when we're in statics, basically things aren't moving, then or if it's moving at a constant velocity, so the acceleration is 0, we can basically change this equation. So if the acceleration is 0, then we have a revised one, and this is just for our static systems. When we get into dynamics, this won't be the case. So sum of the forces equals 0, because in statics we're typically not moving. Equilibrium, just in general, that means that we're either at rest or moving at a constant velocity. So super basic, sum of the forces equals mass times acceleration. We're going to continue to see that throughout this semester. For the free body diagrams, I'm going to go on to the next page. These will really make your life a lot easier if you have a good understanding of these. So basically, with these, this is section 3.2 in your book. Basically, the reason to do free body diagrams is to account for all the forces, all the known and unknown forces. So, why to account for known and unknown forces. A free body diagram is a sketch or drawing that shows the particle free from all of its surroundings. With forces acting on it. The steps for a free body diagram. So we're basically just taking that particle free from everything else and then adding the forces that are on there, so it'll help us solve problems easier. The steps involve, the first one is to draw outline shape, show all the forces, identify all forces, or each force, indicate coordinate system, and include dimensions. To practice this, and maybe we'll go through one of them now. Go through the P 3.1 problems. Pulling that up in my book right now. These will just give you a really quick practice of them. Let's see, sorry, I'm looking for it in the book. P 3.1 is page 96. But basically with these, they want you to draw a free body diagram of the ring and identify each force. So for the first one, they have, maybe we'll just do one of them now. They have ropes connected to the wall. This is point B, this is point C. They tell us some stuff about the dimensions. Oop. Here's the ring, and then it's holding up this weight of 200 newtons. And then they tell us some things about the angles. So this is 30 degrees, and this is a 3, 4, 5 triangle. So to do the free body diagram, and that's the first thing that we're going to do with all these static equilibrium problems. But so this is interested in the ring at A, so we'll do the ring and then put all our forces on it. So we have a force going up from A to C, so force from A to C. And we have a force from A to B. So I'm basically going through each of these and, you know, cutting the rope and then adding a force there to represent that, and doing the same over there. And then we also have that weight going down. And then we'll also draw in things about the geometry. So 30 degrees, 3, 4, 5 triangle, and we'll make an XY coordinate system. So let's do... And that's an example of a free body diagram. So we basically look at whatever it is that we're interested in. Here it was the ring, and then we represent forces for each of the things that are happening to it. It could be that we had a spring or something, and so a spring is still just represented by the force of that spring. And I recommend doing those other problems there. And the answers are uploaded on Blackboard. Let's see. For the next part, we're going to talk about the coplanar force systems. This is section 3.3. And basically with these, it's just that equation that I've already talked about. Sum of the forces equals mass times acceleration. I guess I should say for coplanar, that means that all the forces are on that same plane. So it could be on a X and Y plane. Wouldn't have to be X and Y, but basically in a two-dimensional system for these coplanar forces. So sum of the forces equals mass times acceleration. For these, we're not moving, so the acceleration is 0. So the sum of the forces equals 0. And how we can deal with these is we can break it down into Cartesian coordinates. So basically the sum of the forces in the X in the I direction plus sum of the forces in the sub Y in the J direction, that's going to equal 0. And so because we know that, we can separate the I's and the J's. And we basically get sum of the forces in the X direction equals 0, and the sum of the forces in the Y direction equals 0. So that's basically it with a coplanar force system. So we're sort of building up to this. I think this is a pretty easy next step from the previous one. The next one we were going to talk about are the 3D force systems. So 3D force systems. And basically with this, it's the same. So the same equations. Sum of the forces equals 0. Writing Cartesian coordinates. So the sum of the forces in the X direction, I, plus sum of the forces y direction j plus sum of the forces z direction k equals 0. And then we can just break it up to the sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and sum of the forces in the z direction equals 0. The other thing to note for these 3D problems, obviously it gets a little bit more difficult. Remember when we've already talked about unit vectors will be helpful. So unit vectors. The other thing is just remembering how to write the position vectors, which I think we already talked about. And yeah, I think that's it. So the unit vectors will be helpful for this one. And good luck. Thanks.